So other parameters can also be analyzed in similar lines. If you want to really take a closer look at one particular variable, we could use these kind of techniques to look at box plots or the distribution plots. So it's a kind of analysis called univariate analysis. You're trying to analyze the variable on itself and how that is distributed by itself, right? So now in the next part, we will look at what we call it as bivariate analysis. So we're going to look at how one variable is related to another variable, right? So that's very important, because the very first thing that we want to ensure is that each independent variable, that means each column, each input column, is influencing some or the other way to the output variable, right? So that is one thing that we will look at pictorially and also statistically. So let's look at that. So one of the library that we have, SNS, which is Seaborn. So Seaborn library has something called as pair plot. So pair plot will basically take the data frame and the set of columns as argument, right? So here we are sending the data frame along with the list of columns that we want to do a pair plot for, right? So basically, here I have all the numeric columns as a first parameter, and see how the numeric parameters are dependent on themselves, and also how are they dependent on the output variable, or vice versa. How is it going to influence the output variable? So that sort of information we will try to get from this. And then we use this plot.show to display the graph. And the next one is also here, this is pictorially, it is going to show us if there is any relationship, but whereas this one, what we call it as heat map. So what heat map does is it also gives you a statistical variance value. What do I call it? It's not exactly variance by itself, it's not univariate, it bivariate. So what that means is covariance, right, which is also called as a correlation coefficient, right? How one parameter is closely correlated, or how strongly one parameter is dependent on the other parameter. So that value is given by the heat map. So let's look at both the graphs. Let me first run these and see how the output will be. So since there are high number of columns, it's taking a little while. It should be coming anytime soon. But meantime, I think I have also got these screenshots for these variables. So let me show how this graph looks, right? So what I'm showing you right now is the this is the pair plot. So the pair plot basically takes, on the x-axis, I know this is not so clear, but please bear with me. On the x-axis, we have all the column names that are listed here. You can see wheelbase, car length, car width, car height, and so on. All the parameters are listed here, and the same parameters are also listed on the y-axis. Right? So price is the first one here, but all the parameters are also listed over here, right? And then it plots the variable with the corresponding other variable. Like here, this one, we are seeing how wheelbase is correlated with price. Now how different wheelbase values have their corresponding price values. So we can see there is some relation, some sort of linear relation we can observe, but not so strong. But that's a significant parameter. I think it's indicative of it. Like that, car length is having some sort of a linear relationship here. We can definitely fit some good graphs or the lines, line plot that can actually represent this relationship. Car width is definitely also looking linearly related. Car height is one anti-pattern, so this doesn't look like any way related to the price, right? Because whether you are going right or left, you have too much of variance on the y-axis. So what that means is this is not having any fixed kind of a pattern. So this may not be a very influential parameter for us. So we might look at dropping this parameter as well, but we look at more about dropping the parameters. Then there is curb weight. So curb weight also is definitely looking linearly related, and engine size. And this is one, bore ratio is also doesn't looking like a very strongly correlated with the price. It is not. Stroke is not strongly correlated, and even compression ratio is not is having a different pattern where for some set of values you have both high and low price values, and same here, but that is not giving us any fixed pattern here as well, right? So horsepower is linearly related. So this sort of analysis is what we get from this. Now here you might be seeing a histogram that is coming out, that basically indicates it is univariate, price on price. So all this in the diagonal here, it is the variable on the same variable, so that means that's not bivariate, so that will be a histogram. But otherwise, we can look at um, each parameter and see how it is related to the other parameters. So I have shown you how the output parameter and the input parameters are related in this row, but likewise we can analyze all other parameters as well. But we look at the next graph. In the next graph, it not only shows the pictorial representation, but it also gives you an indication of how strongly correlated they are, right? So let me show you that graph as well. I think meantime this is also printed here. So this is the graph that I'm telling. I think I also have opened it in another window, just so I can zoom it properly. Yeah, it's this one. Okay, so if you look at this, this is something similar. You have this matrix with x values and y values. In the previous graph we have seen pictorial representation, and this one it is giving us a probabilistic value. It's not probabilistic value, I should say. This is called as correlation coefficient. So that indicates how strongly the parameters are dependent on each other. So here if a parameter is close to 1, that is indicating very strongly correlated. If it is close to -1, it is indicating very strongly negatively correlated. That means positive correlation in the sense, if something is increasing, the other parameter is also increasing proportionately. Negative correlation is the opposite, right? So but what we want to look for is all the ones here again, these are univariate, meaning the variable on the same variable, so those can be ignored. But what we really want to take away here is which are those parameters that have high correlation with price, right? Now price, if you see curb weight, engine size, horsepower, and even car width, car length to some extent. So these parameters are having some really good high correlation with the price parameter, so we will definitely include them into our model. But there could be some parameters which might not be looking very high correlation, so we can also take away with these learnings that those parameters may not have really high impact. So we could drop them eventually once we plot the model and we look at their statistical significance, but essentially these may not have really high influence. But apart from analyzing with output, we also want to see, is there any input to input correlation, right? So any input parameter is strongly correlated with another input parameter. Now let's look at this curb weight. Curb weight is almost having 0.88 correlation with car length, right? So these two are redundant. That means if length is increasing, curb weight is increasing, and vice versa. So such kind of parameters will produce anti-patterns in your model. The model may not be very efficient, so we will look at treating them. But otherwise, anything which is close to 1 or 0.9, we want to eliminate one of them. So I will show you one example here. I think it is this one here. Look at this. This is having 0.97 correlation coefficient. That's extremely high. So what are those? This is city mileage per gallon, MPG, and this is highway MPG. So these two are really highly correlated, so we could look at dropping one of them for sure, and then we will go ahead with our model. So this graph really is giving us such kind of a visualization with statistical values, so that we can bank our our decisions based on this, right? So that's the purpose of this graph.